Yes, well, I should say thank you to the organizers for inviting me here to give a talk and for letting me speak after Olivier. I think it's a hard act to follow. He said everything I wanted to say and did it very beautifully, so it was really hard to kind of think about what to put in this talk. But it dawned on me that 11 years ago, I was about 3 months into my PhD, and I was sitting in this very room trying to understand anything I could in a similar introductory workshop at another program at the Newton Institute. So I thought back a little bit about that time, and so I've tried to write this talk for me of 11 years ago. I don't know whether me of 11 years ago will be very happy with my choices, but we'll see what happens. Okay. All right, so this talk really is going to be just kind of trying to highlight and really just say a little bit more about what Olivier was saying. So most of my talk, it's almost exclusively going to be about GLN. Okay, so I'm going to go into a little bit more depth about this, about what he was talking about. Okay, so the setup, like in general, we can just take a finite group and we can look at the characters of the irreducible complex representations of G. Okay, so these form a basis for this vector space of all class functions, so functions that are constant on the conjugacy classes, and they form an orthonormal basis with respect to a standard inner product. Now, as Olivier mentioned in his talk, and it's been mentioned a couple of times, the number of these irreducible characters is equal to the number of conjugacy classes because this vector space also has a basis given by the indicator functions for the conjugacy classes. Now, one can try and ask a question, well, obviously there's a bijection between these two sets. They're finite sets in bijection, but is there any natural traffic you can get between conjugacy classes and irreducible characters? Could you get a natural bijection that satisfied some nice properties? So in general, this is impossible. Okay, but we're going to try and think about, but we've already seen in Olivier's talk that there are, in some sense, some ways for finite reductive groups to get some kind of traffic. Not in general any kind of bijection, but at least some natural correspondence, natural ways to attach conjugacy classes to irreducible characters. Okay, so the basic idea is you can't go directly from one set to the other. That's very hard. So the idea is to introduce an interlocutor. So here, what you hope for is that your group has nice subgroups or a nice subgroup structure. So the idea is that you have subgroups sitting in the middle, okay, and then maybe you can use subgroups to identify conjugacy classes and subgroups to identify irreducible characters, and then sitting in the middle you'll get some kind of traffic going this way. Okay, so we're going to try and use the subgroup structure. So we're going to start not with finite reductive groups, but just with the symmetric group. So Frank already talked about this in his talk. So actually the symmetric group, I'm going to think of it as a Coxeter group with its set of Coxeter generators, SI, so these are the involutions. So you get this Coxeter presentation. This uniquely pins down the symmetric group. So if you look at this as a Coxeter group, then you get these very nice family of subgroups, which are called parabolic subgroups, or in more classical terms, maybe they'd be called Young subgroups. So if you take any subset of this generating set, then that subset will generate a subgroup, which is also isomorphic to a product of symmetric groups, and the sums of the NIs, those will add up to n. Okay, so actually this is giving you a partition. If you if you assume that the NIs are decreasing, weakly decreasing, then this will give you a partition of n. So maybe I'll just say one thing. It's not true here that you can have any arrangement of the symmetric groups. Because you're taking a subset of I, you're only going to get the symmetric groups acting on intervals. So they'll only act on, say, from 1 through k. They'll permute 1 through k, but you can't have any permutations here. Okay, so there are two things to say about this situation. So if you have two of these parabolics, then they're going to be conjugate in the symmetric group if and only if they have the same partition. Okay, and also the intersection of any of these two things is again a parabolic subgroup. So this is relatively important. And this is telling you that if you view the power set of S as a lattice, then actually it embeds into the subgroup lattice of the symmetric group. Okay. Okay, so what can you do? Well, you can actually now take any subset of W, and you can look now at all these parabolic subgroups which meet the set. Okay. If you intersect any of those two, then it's also going to meet the set. And so there's going to be a unique minimal parabolic which meets the set. Okay? And so that gives you a way to take any subset of W, attach a minimal parabolic, and then that'll give you a partition. Okay? So you can do this with any subset of W, but if you do it with the conjugacy classes, then this is going to give you a parameterization of the conjugacy classes using these parabolic subgroups. Okay? So okay, so here you'll get an S3, an S2 cross S2, and an S2. Okay, so this is all fairly standard. Okay, so now I want to think a little bit more. So if I use these parabolic subgroups, I get a natural parameterization of the conjugacy classes in terms of partitions. And so now let's think about the representations. So what we're going to do now is look at we're going to induce the trivial character from this parabolic subgroup. Now here, what I've written is theta lambda for this character, but this depends on I, but all the WI's, if they have the same partition, are conjugate, and so they'll give me the same character when I induce. Okay, so this will give me a family of characters, these permutation representations. Okay, and so it's a standard fact from the representation theory of the symmetric group that inside, so if you look at this permutation representation, there's a unique maximal irreducible sitting inside this permutation representation with respect to the dominance order. So you can label the irreducible characters uniquely, so they're actually all uniquely determined by their multiplicities inside these permutation representations, and the ones that you see below, they're given by the dominance order. Okay, so if you just take the symmetric group S4, okay, then, okay, so these are all the rows of these permutation representations. Obviously, the top one, that's going to be, that's inducing from the trivial subgroup, so that's just the regular representation of the group. So these are all just the dimensions of the representations, okay? So row 4, that's going to be the trivial character. Row 1, 4, that's going to be the sign, so the trivial has to occur in all of these permutation representations. The sign only occurs in the very top one, and if we looked here, okay, at this one inducing from the S3 and S4, so actually Olivier kind of did this example. This is the S3 from S4, and what you're going to be getting is the reflection, the character of the reflection representation. Okay, so that's essentially the natural module when you get a copy of the trivial character and a copy of the reflection character. Okay, so this gives us a nice natural way. So if we use these parabolic subgroups, then we have a nice natural way to label both conjugacy classes and characters. But it's still not really natural. What you kind of hope for, in some sense, is that you introduce this interlocutor, and then once you have this correspondence, then you can kind of somehow find a way to remove these subgroups that you introduce, and then maybe there's a natural correspondence there. But it's not really possible in general, I think, for the symmetric group to do this. Okay. Okay, so let me just say one thing about this. So if you look at this, the matrix of multiplicity, so the dominance order is a partial order, and we can refine it to any total order. So one such refinement is the lexicographic order. So if you take the lexicographic order and you look at the matrix of multiplicities, this is going to be an invertible integer matrix, and so you'll be able to write each irreducible character as a z-linear combination of these permutation representations, and so that's going to mean that the character values of the symmetric group are all integer valued. Okay, because these permutation representations are clearly all integer valued. Okay, so there's a really important duality that occurs in the symmetric group. You have a unique non-trivial linear character, which is the sign character, and that's because the derived subgroup of Sn is the alternating group, which has index 2. Okay, so so if I just tensor with the sign character, then this gives me an involution on involutive permutation of the irreducible characters, and this involution is described on partitions by taking the transpose partition. Okay, so if I write lambda in this multiplicative form, where I record the multiplicities of the parts, then the dual. So if I can write lambda star as a sum of terms. So some of these terms at the end may be zeros, but I'm not going to worry about that too much. Okay, but if I do that, then it's just going to be the sum of the parts. Okay, so just to be super clear, so here's an example of a transpose, and here's an easy way to think about it. So an easy way to do this is you just take the Young diagram of this partition. So you write the parts 5, 4, 4, 2, and there's a natural way. You're just going to reflect this in the line in this line, and then when you reflect, you'll get the transpose partition. Okay. All right. So now I want to move on to back to finite reductive groups. So this is where we're really this is what we really want to consider. So just like in previous talks, I'm going to let F be an algebraic closure of Fp, and I'm going to consider GLN F. So actually, this is going to be this algebraic group, so this infinite group. And then I have this Frobenius endomorphism, which is this Galois automorphism, which I'm extending to the whole of GLN. Okay, and then when I take fixed points, this is going to be GLN FQ. Okay. So we have these special subgroups. So Frank also mentioned these in his talk. All right, so we have this maximal torus of diagonal matrices, and this Borel subgroup of upper triangular matrices, and we have a quotient. So W, this quotient is the symmetric group. If you take the normalizer in G of T mod T, that's going to be isomorphic to the symmetric group. And this choice of Borel subgroup uniquely determines a set of Coxeter generators inside the Weil group, and that's exactly the ones that we started with. If I choose this Borel, then I'm going to get these I plus 1 Coxeter generators. Okay, so we can also do now parabolic subgroups for GLN. Okay, so actually we've already seen these before. So they came up in Ellen's talk. She talked about them as stabilizers of flags. So that's one way to think about every parabolic is going to be the stabilizer of a flag. But here we can just say we can take each subset and we can associate there's going to be a unique subgroup which contains B and is a semi-direct product of a Levy factor, this Li, semi-direct product its unipotent radicals. So the Li, just like in the symmetric group case, right, this is a direct product of general linear groups of smaller on smaller dimensional vector spaces. And now inside this Levy, if I look at NLI of T mod T, so that sits naturally inside NG of T mod T, then that's going to be exactly the parabolic subgroup we had in the symmetric group. Okay, so we can look again at this lemma about conjugacies and these subsets. So things are a little bit different for these parabolic subgroups inside GLN. So now, actually, if you take these full parabolics that contain the Borel, then two of them are going to be conjugate if and only if they're equal. Okay, it's a slightly stronger conjugacy statement. But we get the same thing for the levies. So you have two of the levies are going to be conjugate inside G if and only if they have the same partition, so they have the same general shape. And again, the intersection of two Levy subgroups is again going to be a Levy subgroup. Okay. So we can do the same idea as we did before, where we take any subset of our group, and now I can associate a minimal Levy subgroup which meets O. Okay. So in general, if you want to do this labeling, you want to really just look at things that meet O, not necessarily contain O, because you're looking at too small a set of subgroups to actually do containment. Okay. So, but in this way, you'll you'll associate to each subset partition. And if you do this with conjugacy classes, you can associate to any conjugacy class a partition. So if you take, for instance, if you take a conjugacy class and you think about what would have the partition 1, 1, 1, 1, 1, so all ones, well, that's going to happen if and only if this minimal Levy subgroup is T, is your maximal torus. So that means that it's going to be that partition if and only if your element is semi-simple. Okay? So really, this is kind of a nice way of encoding the Jordan normal form, okay? Or at least giving you some idea about what the shape of the Jordan normal form is of your of the elements in your conjugacy class. Okay? So if we just restrict to unipotent classes, so we've seen these unipotent matrices, if we restrict to unipotent classes, then this is going to be actually a bijection between partitions and unipotent classes. Okay, so for instance, the one with a single Jordan block, that's going to be an O4, and the one with two Jordan blocks is going to be an O22. So I'm going to call O lambda the unipotent conjugacy class where the elements have Jordan normal form parameterized by lambda. Okay, so now we can do the same thing. We can try and do the same thing for representations. So let's try and cook up some representations. So we can do the same thing as we did before. So let's induce these parabolic subgroups. So we can look at the coset, these representations on the coset spaces. Okay, we can do that for every I. Now, again, I've written that I've put R lambda here to indicate that it's parameterized by a partition, but actually that's maybe less clear because the parabolics of maybe aren't conjugate. But really, this is secretly a different type of construction. So this is a construction known as Harshchandra induction. So actually, this induction, I can think of it, so the Levy is both a subgroup and a quotient of the parabolic. So if you have a character of the Levy, if you think about it as a quotient of P, then you can inflate to P, and then you can induce. So if you inflate the trivial character, then you get the trivial character. Okay, and so actually, this induction is just inflation induction from the Levy. Now, if we do it like this, then actually, because the Levy's a conjugate, that'll mean that these induced will get the same permutation characters when we induce. So that's fine. So these permutation characters will be the same. And I should mention, so I think this will come up later on in the week, so I wanted to mention it, that we also have a dual construction, which is called Harshchandra restriction. So there, really, it's exactly the duals of doing inflating and inducing. You're restricting, and then you're deflating. Okay, so this gives us, so Olivier kind of mentioned this before. So if there's this setup where you look at he looked at the induction, or the Harshchandra induction from the torus. He looked at RTG1, and he saw that he said that the endomorphism algebra of that of the representation was isomorphic to the group algebra of the symmetric group, and so the summands were parameterized by irreducible characters of the symmetric group. So actually, you can say a little bit more that if you go from the parabolics, actually the multiplicities of the unipotent characters in these permutation representations coming from the parabolics, they're actually the same as the ones you would get if you looked in the symmetric group. Okay, so it's actually a very strong statement. The multiplicities actually all match up. So because every irreducible character of the symmetric group is uniquely determined by its multiplicities in those permutation representations, the same is true for the unipotent characters. So you have a unique way to label the unipotent characters in the symmetric group, in GLN, just by looking at these permutation multiplicities. Okay? So if you do this well, okay, I mean, just like before, well, the trivial character's got to be chi-n because it's got to occur in everything. And then you'll get, at the other end, you'll get this Steinberg character whose dimension is q to the n minus 1 over 2. Okay. All right, so you can't quite do exactly the same argument as before. In the symmetric group case, we got that these things were all integral valued, but actually you can get this here for using a slightly different argument if you look a little at Galois actions. So if you allow yourself to act with the Galois group, so the Galois group is going to permute irreducible characters. So if you look at these R lambdas and the chi-mus, and then if you have sigma in the Galois group, then it's going to preserve this in a product. And this is all the values of this permutation representation are integers. So it's going to be fixed under any Galois automorphism. So that means this thing is going to be just R lambda. But then you know that that character is uniquely determined by its multiplicities in there. And so actually you get that chi-mu is going to be fixed by the Galois automorphism. Okay, so it's going to be invariant under all Galois automorphisms. So these kinds of I mentioned this because there's some problems, and I'm sure maybe Britta will talk about it a little if she's talking about counting conjectures. There are some issues about trying to understand actions of Galois automorphisms and in general actions of just the automorphism group on irreducible characters for finite reductive groups that have proved to be very difficult. And having statements like this, where you have a unique way to pin down these characters, is very helpful in trying to settle these the issues with these actions. Okay, so I want to mention one more thing. So if we look at the values of these permutation characters, actually, so in the symmetric group case, there are lots of zeros in the symmetric group case, but that's not the case here. And the issue is that this parabolic, it contains a Borel subgroup. Okay, so every element's going to be conjugate inside a Borel subgroup. So you're going to get lots and lots and lots of non-zero values. So I would like a construction which has more zeros. Okay, 0 is my favorite integer. So let's think about this other extreme. So with these parabolic subgroups, you have the Levy, but then you also have the unipotent radical. So I personally am very afraid of P groups. And so I put the word reductive in front of everything so I don't have to deal with P groups. So this is kind of dangerous territory because now we're kind of heading towards P groups, and so I like to try and avoid them. But we're inducing to G, and so hopefully when we induce to G, we're going to get rid of a lot of the nastiness of P groups. The group G will kind of absorb all that nastiness and make it nice for us again. Okay, so all right, so why don't we try and look at the induction from this unipotent radical of the parabolic. So I'm going to pick actually now my favorite unipotent radical. So I'm going to for each partition, I'm going to pick specifically this parabolic subgroup where the Levy factors are actually given exactly by the lambda i's. Okay, so this is going to pick out exactly a u lambda for me. Okay, so this is the unipotent radical of a parabolic. Okay, so a natural question, well, if you want to understand whether this is non-zero, you need to know when is an element going to be conjugate inside u lambda f for some g. Okay, so let's try and answer this question. So actually, we're going to come back to this question about this order that Olivier mentioned, this closure relation on the classes. So firstly, let's just recall what Olivier told us. So if you have an element in O mu, so it's a unipotent element with Jordan blocks parameterized by mu, and the same B has parameterized by lambda, then A is in the closure of the G class of B if and only if mu dominates lambda. Okay. Now, actually the G, so in the algebraic group, so over F, the algebraically closed field, AG intersects, meets U lambda, that's if and only if mu is dominated by the transpose of lambda. So there's actually a duality going on the unipotent classes. So I want to delve into this a little bit more and maybe just kind of make clear exactly why this closure relation exists. It's not a very, it seems a bit strange. To me, I found it very strange when I first saw it because it doesn't seem to have anything to do with polynomials. I mean, closure relations should mean closed sets, so you should be coming up with polynomials, and I don't see how you do this way. So let's delve into this a little bit. So what we want to do is try and characterize the Jordan normal form in a way that's better adapted to trying to solve polynomial equations. So one way to try and think about this is, how do you characterize a Jordan block? Just a single Jordan block, big, massive Jordan block. Well, one way to try and identify it is to look at powers of the Jordan block. So if you take powers of the Jordan block and you look at the rank of the matrix, then actually all its powers up to n have non-zero rank. Okay? And actually it has a very nice expression. It's not difficult to calculate that the rank of this power is n minus k. So here I'm looking at this nilpotent matrix because it's easier to multiply nilpotent things together than unipotent things. Okay, so this gives us a way we can kind of think about this. So if you take a unipotent matrix now in GLNF, then what you can do is for each k lying between 1 and n, you can subtract off the identity. You'll get a nilpotent matrix, and now you can look at the powers of that nilpotent matrix and calculate its rank over F. So actually you can characterize the Jordan normal form using this procedure. So you actually have that a matrix will be contained in O lambda if and only if it's these RKAs are given by this expression with the transpose partition. So you can see this is already right here, right? So the partition labeling this is n, because it's a single Jordan block, and its transpose partition is 1, 1, 1, 1, 1, right? And that k, that's just the sum of 1 from I equals 1 to k. Okay, so this is one way to characterize it. So the reason why this is coming up here, right? So in terms of these multiplicities, what is that counting? That multiplicity is counting the number of Jordan blocks over a given size, right? Because at some point, if you have a Jordan block of small enough size and you raise to a power, it's going to go to 0. So that's what you're trying to keep track of in this partition. Okay, so let's just stick that up there. So now let's look at the closure relation. So I'm going to cheat a little bit, so you have to do a little bit of work to see this. But if you have two unipotent matrices, then A is going to be in the closure of B if and only if the kth rank of A is less than or equal to the kth rank of B for all k lying between 1 and n. Well, you can look at this expression for the k ranks, okay? And if you bring that down here and here, so you're going to get n minus a bunch of mu I stars and n minus a bunch of lambda I stars. So you're going to swap those over. So that's going to be, you're going to be exactly getting the dominance relation on lambda star versus mu star. And now there's a little fact about partitions that the transpose actually reverses the order, the dominance order. So you have the mu is dominated by lambda if and only if lambda star is dominated by mu star. Okay, so this is a way to try to actually see what this closure relation is. And you can. So why does this look slightly better? Well, you can. This kind of condition about RKA less than or equal to RKB. Okay, you can imagine that actually this is a union of sets where you want the rank of that power to be equal to a fixed number. okay, less than or equal to whatever this is going to be. So you'll actually have just a finite union of sets, of closed sets, which must be closed. Okay, so it's not difficult to see that these rank conditions will be given by a polynomial in the matrix entries. Okay, so this is this closure relation. So now there's a very nice result, which is Richardson's dense orbit theorem, which says that O lambda star is the unique unipotent class such that the intersection with U lambda is an open dense subset of U lambda. So this is a result which is a very general result due to Richardson, which tells you if you know there are finitely many unipotent classes, then if you take any parabolic and then the unipotent radical will meet exactly one unipotent class as an open dense subset. So this idea is these kinds of unipotent classes are called Richardson classes. So what we're seeing here, so we have this natural involution on partitions by taking the transpose. So in the representation theory of the symmetric group, this is realized by tensoring with the sign character. In the theory of unipotent classes, this is given by two different ways of thinking about unipotent classes. So you can take what's called the Bala-Carter approach, which is we do exactly what we did. We take the smallest Levy subgroup which meets the class. This is the Bala-Carter approach. So if you were thinking about, say, the trivial unipotent class, then in a Bala-Carter framework, you would be looking at your Levy being a torus. Okay? And that would be how you parameterize it. In the Richardson setting, the Richardson setting says, look now at the unipotent radical and try and trap your class inside the unipotent radical. So if you're talking about the trivial class, that means, so your U lambda, you want that to be trivial, which means you want lambda to be really big, so you need that to be n. Okay? So this is two dualities on unipotent classes. So this is this is very special to type A. Outside of type A, it's not true that every unipotent class is a Richardson class, but there is always a Bala-Carter labeling of unipotent classes. But there are other things you can do. The Richardson method is still very important in general. Okay, so I want to come back. I want to circle back now. So we're keeping in mind these permutation representations on the cosets coming from this unipotent radical, from this P subgroup. So at least I know now that when an element is going to be non-zero in that permutation representation, where it's going to have non-zero character value, because I can say when something's conjugate inside that U lambda. But actually, I want to think a little bit about the duality. So we've had duality in the symmetric group, we've had duality on unipotent classes, but what about the chi lambdas, the characters of GLNQ? I mean, there should be a duality there, because you can just take chi lambda and send it to chi lambda star. Now, is that just something notational, or is there something more going on? And actually, there is something more going on. So we have a special duality in the representation theory of finite reductive groups, which is known as Alvis-Curtis duality, or really more formally, it should be Alvis-Curtis-Kawanaka-Lusztig duality, but life is too short to say four names at once, so we'll say Alvis-Curtis duality. Okay, so how this is necessarily defined is not super important, but I just wanted to put the definition up because it's relatively simple. You use these Harishchandra induction and restriction maps. So what you're going to do is you're going to restrict to the Levy, and then Harishchandra restrict to the Levy, and then Harishchandra induce back up to G. Okay, but there's some alternating sign here, and this is to do with some FQ rank of the parabolic. But I don't want to get into this. But it's not just it's not going to send necessarily characters to characters, because there are signs involved. So the main theorem is that this map is an involutive isometry on the space of class functions. So I'll get with that in a minute. So what that means is that if you take an irreducible character, then up to sign, the Alvis-Curtis dual is actually an irreducible character. And so let's do this, because it's not very hard, and it'll also explain what involutive isometry means. So, okay, so, well, involutive means that it squares to the identity, so you have the dg squared of chi is equal to chi. Right, so that's going to mean that okay, this is going to be true because they're equals, they have multiplicity 1. Now, this is right, this is an isometry, which means it preserves the inner product, and it's an involution. So that means this is going to be this is going to have inner product 1. Now, dg chi you can write as a sum of irreducibles. Okay, and the inner product that's going to be the sum of the squares of the ensides. But this sends a character to a virtual character, so a z-linear combination of irreducibles, and so you have a sum of squares of integers that equal 1, and so the only possible solution is that exactly one of them is non-zero and equal to 1, and so the square must be plus or minus 1. Okay. So it's once you kind of know this property, actually showing that you get this involution is very easy. And well, I mean, if you go back to the fact that this, if you go back to the fact that the unipotent characters are characterized by their multiplicities in these permutation representations coming from the parabolics, you can actually work out the effect of dg on those characters, and you can conclude that for any partition, actually Alves-Curtis duality sends chi lambda to chi lambda star. Okay? So there's no sign involved in this case, but it's very special. There's usually a sign involved somewhere. Okay, so there's this special kind of duality. Okay, so now we can come back. So I've kind of taken a slight detour. So I'm going to use this duality now to look at these induced characters. So the problem with these induced characters is they're really hard in general, and actually this is kind of tricky if you want to look at this induction from u lambda f to gf. So I don't really want to look at all the characters because they're too hard. I want to identify a special collection of those characters. So I'm going to write this. So there's a construction which is due to Kawanaka of these characters, and what I'm using here is a characterization of them which is due to Gekken-Hazard, which is a little easier to understand. So I'm going to talk about something which is gamma lambda. So because of this duality on the unipotent classes, I'm going to induce from u lambda star. Okay, so all right, because that's the so that means that O lambda will intersect u lambda star as a dense open subset. So it's Richardson for that unipotent radical. Okay, so there is a way to cook up a character, not necessarily irreducible, of u lambda star f. So if you let gamma lambda be the induced character, then the dimension, the p part of gamma lambda 1. So obviously this is the dimension of this thing is going to contain the p prime part of the order of G, because this is always, because this is a p subgroup. So we're only really interested in the p part. So the p part is going to be q to the d lambda, and this is exactly what Olivier wrote down when he talked about the unipotent support. Okay, so it's actually this d lambda is half. He wrote it slightly differently. I'm putting the dimension of On, that's the dimension of the regular class, but that's just n times n minus 1 over 2. No, I didn't want that. No, I did want that. No, that's fine, it's fine. No, it's n times n minus 1. That's fine. Okay, so we already know this property. We've already seen that gamma lambda of u non-zero. That implies that that UG has to be below O lambda in this partial ordering on the unipotent classes. Now, what's really special is that the Alvis-Curtis duality now, if I apply that to gamma lambda, then actually O lambda must be contained in UG. So this Alvis-Curtis duality is actually, there's this, you can think of this as like it's an it has order reversing properties on character values with respect to unipotent classes. Okay, so this is actually, this last statement is very powerful. Okay, so, and I should say that in general, you can just, these three properties, no matter how we're going to define these characters, which are called generalized Gelfand-Grave characters, these three properties uniquely determine when a character is a generalized Gelfand-Grave character. So anything that satisfies these three properties will be 1. Okay, so these are the key properties that you need to know. Okay, so what I want to do, okay, let's look at an example. So if I take lambda equal to 1 to the n, then I'm inducing the trivial character from the trivial subgroup, and that's just going to give me the regular representation, and the p part is going to be q to the n times n minus 1 over 2, and that's exactly right. I want to subtract off 0 here, okay, because I'm looking at the trivial class. So if I look at the other extreme, then I'm going from lambda equals n, so this gamma lambda, I'm going to be inducing from u1 to the n, so that's actually the CeLO P, right? That's actually the CeLO P subgroup of GLN. So if I do this, so okay, what eta should I be using? What character should I be using? Well, let's look at the first property. So the first property says that gamma lambda of 1, well, I know it should be dim on minus dim o lambda. Well, lambda's n, so this has to be 0. So that means that this thing has to have p part equal to 1. Okay, so this is p prime, so the p part's determined by eta 1, so that means that eta 1 has to be 1, so eta has to be a linear character. But it's not true that you can't just take any linear character. If you take the trivial character, it's not going to satisfy this property. So you only want to take certain characters. So which ones do you want to take? Well, if you look at the quotient of the unipotent radical, the CeLO P, if you quotient out by the derived subgroup, right, we're just interested in this because it's linear, then this is going to be isomorphic to a direct sum of copies of the additive group of the field, and minus 1 copies. And what you want, the only property you need is that if your character is going to be a direct product of characters of those additive groups, and you just want that none of them are trivial. Okay, just as long as you assume that none of them are trivial in each one, so it's called a non-degenerate character, then you'll get this Gelfand-Grave property. And there are loads of choices you can make, but when you induce up, they all become the same character. Okay, so there's a lot of flexibility in your choices that go into it, but what you get out at the end is relatively rigid. Okay, so what I want to do is just look at these properties and see what effect they have on the multiplicities. So if I try and now, I want to look at the multiplicity of chi mu star in gamma lambda. Okay, so chi mu star, well, I know that's the Alvis-Curtis dual of chi mu. Okay, so I can replace that, and this Alvis-Curtis duality, that's an involution, so I can pass the dg over to the other side. Now, there's a well-known formula for calculating the inner product of two characters. Okay, it's given by averaging over the group. So let's try and look at this now. Well, if this term, so if this is non-zero, then there has to be an element inside here where this term is non-zero. Okay, so if the dual is non-zero, then I know from the previous properties that O lambda's got to be in the closure of UG. Okay, and actually if this is non-zero, then Olivier mentioned this is unipotent support. That actually tells you that UG has to be in O mu. So that means that O lambda has to be in O mu. So actually lambda has to be dominated by mu. And maybe if I write it a little differently, because actually I started with mu star, so if I dualize, that's going to say that mu star has to be dominated by lambda star. So there's actually a theorem of, so the theorem of Kawanaka says the following. So for each partition, there's chi lambda is the unique unipotent character such that if you look inside the multiplicity of chi mu inside gamma lambda, if it occurs in there, then mu has to be dominated by lambda star. Okay, so this is exactly what we were doing for exactly how we were doing the characters of the symmetric group. And actually, there's a little extra fact that chi lambda star will occur inside gamma lambda with multiplicity 1. Okay, so this is a different way of looking at these characters. So in general, if you have a problem, you want as many viewpoints as you can. Okay, we had already classified. You can classify the characters of GLN, 6 different ways, but it's really great to have as many viewpoints as you can. This offers another way of looking at it. So actually, this gives you. So I've kind of cheated and reversed everything in the way it was really done. So the unipotent support, if I think about this original problem, that's a very natural way. It's completely natural to associate to an irreducible character or conjugacy class of the group. It's so natural, you just read it off the character table. It's completely intrinsic to the character. So this actually gives me a way to going via my subgroups. If I go via these U lambdas, then I actually get a class in this way. It's the dual class. It's the O lambda star. But it involves this subgroup business. But actually, when it was proved that the unipotent support exists, what you first show is that this class exists, and then use the existence of this class to show that to get this natural unipotent support occurring. So actually, the existence of these representations is incredibly important to exhibiting that this unipotent support exists. Okay, so maybe I'll just mention this. So just like before, actually, so if you take this, if you look now at the matrix of multiplicities, then this has a very strong property. It also has this, so if you order with respect to the lexicographic ordering, so just total ordering refining the partial order, then the matrix of multiplicities is lower unitriangular. Okay, so it's invertible over the integers. Actually, that's had a surprising number of useful properties. In particular, it has applications to modular representation theory, because these gamma lambdas actually turn out to be characters of projective representations in non-defining characteristic. Okay, so let me say maybe a little bit about, I don't want to say too much about this construction, about how we choose eta, but let's say a little. So, okay, so U is U lambda, so U lambda F is a dreaded P group. So that means it's solvable. Okay, so the thing about solvable groups is, right, that means that you have this derived series that is going to terminate, and it has these nice abelian quotients. So you can think of this as you're really grading, you're kind of grading your P group via this series. Well, you can actually look at other gradings of U, and in general you want to use a grading which comes from what are called weighted Dynkin diagrams. So this is coming from the theory of unipotent classes. So I won't do this in general, but let's just look at some of these weighted Dynkin diagrams for GL4F. Okay, so you're going to have, so the Dynkin diagram of G, which in this case is an A3, and then the weighted Dynkin diagram, you put 0, 1, or 2 on the nodes. Okay, so you don't do not every combination will occur, but these are the ones for the classes in GL4. Okay, and then you have zeros on the. Okay, so when the class is what's called even, which means when all of these nodes either have a 0 or a 2 on them, then you're actually always going to use a linear character, which is why I kind of labeled that maybe in a funny way. The U2 actually there is going to correspond really to the subgroup that I want to take. I want to quotient out by that, and then actually use a linear character. But when this happens, and actually there are ones on the diagram, that's not what you want to do. So in general, in that situation, you want to do something a little bit more interesting. So in the theory of solvable groups, there's very nice work by Isaacs and people like this, I mean, from a really long time ago, looked at getting characters of solvable groups by using alternating forms and looking at corresponding representations of symplectic groups. So there are interesting symplectic structures that you can put on the unipotent radical and actually use those to produce these characters. And the characters aren't actually irreducible for the radical. They're irreducible from a subgroup, and you induce up to the whole radical. So it's a little bit involved, but it's kind of some nice things going on. Okay, so I have 10 minutes left. So this is my attempt to now try and talk about character sheaves in 10 minutes. We'll see how this goes. So I mean, if you think about this result, and now you think, okay, I have a character, an irreducible character of G, of GLNQ. Now, if you look at imagine you look at the character table, and you look just at the bits which contain you look at the rows corresponding to the unipotent characters and the columns corresponding to the unipotent classes. And now you order everything with respect to the lexicographic ordering. The unipotent support is going to tell you that it's almost like triangular shaped, that part of the character table. I mean, that's just freaky. That shouldn't happen. That's very surprising. And it's not clear why really is this so closely related to these closure relations on unipotent classes. So Olivier actually said this unipotent support, when you're non-zero, if you have a character which is non-zero on a unipotent element, then U has to be in the closure of a unipotent class. That means that the characters of the finite group actually detect the closure relation on the level of the algebraic group. I mean, that's incredibly surprising. There is a priori no reason why that should happen. Okay? So you have to think there's something more going on, and there is something more going on. So there's a beautiful theory, which I'm going to try and describe in a very short period of time. And I just want to give some hints as to what's going on in the background. So I'm going to switch gears to, I don't want to work over the complex numbers anymore. For topological reasons, I want to work over an algebraic closure of QL, so the aladic numbers. So I'm going to work with L a prime different from P. And I'm going to work in a category which is called the bounded derived category of QL bar constructible sheaves on G. So this has a lot of adjectives, and we're not going to get into what this really is. But let's just say that objects in this category are complexes of sheaves. Now, you should take complexes of sheaves not to be literally. It's not to be in a literal way. It's actually a little bit more complicated than this, but it gives you the right idea to think about them as complexes of sheaves. Okay, so one important thing for us is that if you take an object in this category, well, you can look at its cohomology sheaves, and so each of these is going to be a sheaf, and the cohomology sheaf, you can look at the stalk. So this is going to be a finite dimensional QL bar vector space. So you're taking an element in G and associating to it a finite dimensional QL bar vector space, which is good because we're representation theorists and we want vector spaces. Okay? Now what we're going to do is take this object and we're going to spit out functions on the finite group. Okay, so you remember we have this Frobenius kicking around. Okay, so this actually naturally induces a functor on this bounded derived category. It's called the pullback functor. Okay, so the thing about this category is that it's defined purely at the level of the algebraic group, but we want to do things for the finite group. So there's going to be lots of objects in this category which aren't really relevant for us in terms of this finite group. So we have to look at the ones that are relevant. So we're just going to look at the ones for which there's an isomorphism from Frobenius pullback to itself. Okay? So if you take an element in this, an element fixed by Frobenius, then this pullback function is very natural. If you take the stalk of the ith cohomology at the of f star a, then that's actually just the cohomology at f of x. So if x is fixed by Frobenius, so it lands inside our finite group, then actually this stalk is actually the same as what you started with, hx I of a. So the isomorphism we picked from f star a to a, that actually induces an isomorphism from this vector space to itself, okay? And from the pair of this object and this isomorphism, we get what's called a characteristic function, okay? So, and the way you do that is you take an alternating trace of the isomorphism on the various stalks of the cohomology sheaves. Now, this is actually going to be a class function, and the reason why it's a class function is all contained in the words. I would have been contained in the word if I put it on there. There should be the words G equivariant inside the definition of the bounded derived category, because I want these things to be equivariant with respect to the conjugation action of G on itself. Okay? So this is that equivariance is going to mean that this thing is a class function. Okay? So you can think of this as a very fancy gadget for producing class functions. Okay, so one of the kind of key things that we need to think about are what are called local systems. So if you have a conjugacy class, so if you think of the best G invariant subset of G that you can think of, the smallest one's going to be a conjugacy class if you're acting by a conjugation. So one of the basic things that we have to deal with when we're working in this category is we have to deal with what are called local systems on these conjugacy classes. Now, local systems, if you see local system, you should think representation. Okay? This is like so here what's happening is that you have the component group of the centralizer which occurred in Olivier's talk. So in the case of GLN, these would be trivial, but in general they're non-trivial. And so you should think of the local systems on the orbit. It's like a fundamental group calculation. So you can think of this as like a fundamental group on O. So let's say you have like an algebraic group. If you have an algebraic group acting, I don't know, let's say you have an algebraic group acting on an algebraic variety, it'll permute the irreducible components, and you know that the connected component will always act trivially because if there are finitely many irreducible components. So it's kind of a similar idea here. This is why you're kind of you can think of the connected component as kind of acting trivially. Okay, so what are easy to understand are local systems. So what you want to do is take a local system, which is essentially a representation of a finite group, and you want to make objects inside DGG. So what I'm going to look at is just look at the set of pairs where you take a unipotent class and an equivariant local system on that unipotent class. So think irreducible representation of the component group of the centralizer. Now, the most important construction in this category is what are called intersection cohomology complexes. They take something easy, your local system, which is just like a representation of a finite group, which is on the class. Now you can take the closure of the class. You get a nice big closed set. And this IC is, in a functorial way, extends that local system all the way up to an object on the closed set. So this is actually producing now an equivariant object on this closure of the class. So I'm shifting. Remember, these are complexes, so I'm allowed to shift complexes, and I'm shifting because I want this to be a perverse sheaf, but I don't really want to talk about perverse sheaves, so you can just ignore the shifts. They're not going to be super important, but they should be there. Okay, so you have this construction, this IC construction. So if you look at a conjugate class and you assume it's F stable, and that the local system is actually isomorphic to its Frobenius pullback, so this is like F stability. It gives something for the finite group. Then you can look at its corresponding characteristic function. And built in to this construction is the closure amongst the unipotent classes. This is only going to be non-zero when U is in the closure of O. Okay. And actually, if you're in O, then you're just going to recover back an isomorphism on the local system. So it's really recovering. You could think of this on the level of characteristic functions as something which is you get lots of new information on the closure, but on O, you still just get the same representation that you started with, that you chucked in. Okay. So how does this character, well, I said it should be related to a character of the component group. So roughly, what this should mean is, I mean, if you take a geometric conjugate, which is F-stable, so you're conjugate by an element in the algebraic group over the algebraic closure, but not necessarily over the finite field, then G inverse F of G is going to be in the centralizer of G of U. So this is this image under the Lang map that we've seen. And then actually this trace is essentially going to be given by the character value of the image in the component group. Okay, so that's actually how this is really related. So you really do recover this xi. Okay, so let me zero it. We're almost there, so let's just wrap it up. Okay, so in this construction, Lusztig gives a version of induction. So you can actually induce the easiest. We have a version of the trivial representation, which is called the trivial local system, and you can look at that on a torus, and you can induce it geometrically induce that from T up to G to get a nice big complex on G. Now, just like when Olivier did this, the endomorphism algebra of that object is actually also isomorphic to the group algebra of the Weil group. And it's just a standard theory of, like, you can just, it's purely categorical construction that'll give you a parameterization of the irreducible summands in terms of the irreducible characters of W, and there should be some multiplicities there, which I forgot. But you're going to get a labeling of these summands by the irreducible characters of W, just like in the usual theory. And what Lusztig showed that if you take one of those summands and you restrict it now to the unipotent variety, then actually you get one of these ICs on the closure of a unipotent class. And this actually gives you an injection from the set of irreducible representations of W into this set of pairs. That injection is actually what's known as the Springer correspondence. Now, why does this explain what we're doing? So actually, if we think just about GLN, then it turns out that if you take the characteristic function of one of these k rows, then actually that characteristic function turns out to be a genuine unipotent character. So the reason why things are so nice in GLN is actually because the irreducible characters can be realized purely geometrically in terms of character sheaves, where you actually see these closure relations being built into the construction from the get-go. So in some sense, this explains this phenomenon in GLN. And more generally, you're not too far from, like, the character sheaves and irreducible characters in general are not too far away from each other, which is why you get lots of nice geometric statements occurring for characters. Okay, I will stop there. Yeah, let's say yes. It'd be a bit damning to say it was a really bad talk now.